Chapter 4, Supporting Processors and Upgrading Memory. Main objectives for this chapter is discussing the different types of processors, also explaining the characteristics and the main purpose. We're going to talk about how to install them, how to upgrade them. We're also going to learn about the different kinds of physical memory and how they work. This also includes how to upgrade memory as well. So, last week we talked about motherboards. Now we have to talk about our processors. Our processors are essentially the brain of the computer. There are two major manufacturers of processors, Intel and AMD. They are not the only manufacturers, they're just two of the main companies. So when we start talking about characteristics of a processor, what a processor is, we have to talk about a few things. First of all, we have to talk about the speed of the processor. That's typically known as the clock speed. And that is the clock speed that the processor will support. How fast can the processor work? So, how do we actually find the processor speed? And that actually is a base clock speed times the ratio. We're going to talk about that a little bit later, but our processor speed is just taking our base rate and timing it by a ratio. Again, we're going to talk about that there in a little bit, but I want to point that out now. Next, within our motherboard, the socket that the motherboard has, which will determine the processor that we can use with that motherboard, as well as what chipset that motherboard has. Next, processor architecture, or the overall design of the processor. Lastly, its multi-processing abilities or capabilities. So we have three major types of multi-processors ability, and that is dual processor or dual CPUs, and that is where we have two CPUs per computer on one motherboard. Another example could be a multi-core processor, and that is one processor with multiple cores. Lastly is a technique called multi-threading, and that is actually having one core do multiple tasks. So you can actually have multiple cores per processor, and each of those cores having hyper-threading. So instead of processing one task, they can do two tasks at once. Some of the features that may affect the processor's performance, that is the memory cache. That's how much fast memory is on the processor. That also includes the memory features that the motherboard supports. If it has support for virtualization, or if it has integrated graphics. That is, the processor actually does the processing of the graphics. You'll normally find this if there is no dedicated video card. If it's a built-on video card, it's integrated graphics typically. However, if there is a add-on or third-party video card, it'll be not integrated. Essentially, where is the graphics being processed? Is it on the card or on the processor? So, when we actually start talking about the architecture of the processor, we have to take a look at how it works. And how it works is broken into three major components. The input-output unit, and that is, it manages the data, the instructions, and the threads entering and leaving the processor. Next is the control unit, and that manages all the activities within the processor. And last, the ALUs. Those are the ones doing the comparisons and calculations. Essentially, those are what make up the processor. Now we have to talk about the overall storage of those processes or threads in the processor. And that is broken down into three other areas: registers, cache, and our bus. So our registers are small holding areas on the processor chip. It's extremely fast temporary memory. Next would be the internal memory cache, and that is again just extremely fast, but not as fast as the registers. Lastly are the buses, and those are the actual connections between the cores of the processor and other cores, as well as to other things outside of the processor. Here's an example of a standard Pentium a while back. The yellow connections, those are the buses. Our ALUs and our control unit, that makes up one core. Each ALU has its own set of registers dedicated to those. However, the internal cache could be shared between the entire core. There goes the control unit and then to the input-output before it actually connects to the rest of the bus, which would take it to either the memory or the north bridge. But those are our communication pathways. So now we have to talk about the speed. And again, we've already talked about the processor speed actually being the frequency or the bus speed times the multiplier. And that's actually how we get our processor speed. Before we go too in depth about that, I do want to bring up the fact that our processors, now the pathways that connect to them are either 32-bit or 64-bit, and essentially that is how many bits of data the processor can handle at a time. If it's only 32, it's 32, it's max. However, if it's 64, then it can handle 64 or 32. So let's talk about our processor frequency a little bit more in depth. So normally we have a multiplier of some number, typically under 20, and we have our bus frequency. Our bus frequency normally is around 200. And so what we do is we take that 200 and we times it by a multiplier, and that's how we figure out our processor speed. So if we have a bus frequency of 200 and a multiplier of 14, for example, our processor speed would be 2,800 hertz, or 2.8 gigahertz. So as we talk about our processors, normally we refer to them either 32 or 64. There's this hybrid, but again, as long as it's a 64-bit, it can handle 32 or 64. The 32 can't handle 64, but the hybrid is kind of what a 64-bit processor typically is. An important note. Notice here the 32-bit is also known as an x86. All that is, in the early 90s, we had our 286s, our 386s, our 486s. Those are all 32-bit process architectures. Now we have our 64-bit processors, so it's the x64. The 86 really means nothing. It was just that was what we used to call our processors, and the name just kind of stuck. So now let's talk a little bit more in depth about the memory or the temporary storage for the processor. So typically it comes in three different types: L1, L2, and L3. So essentially when we talk about the registers are quick, fast. They're the fastest in memory. Next is L2, then next is registers, L1, L2, then L3. L3 is the slowest. However, keeping in mind these are all typically faster than the traditional memory for the rest of the system. These are just special memory for the processor. Each core in a processor has its own L1 and L2, but they will share L3. All this really does is help improve performance. Next, depending on the architecture, the memory controller could be part of the processor package. And what it does is the memory controller controls access to the system's memory. So that's not our L1, L2, and L3, that's our traditional RAM. What that allows us to do is it allows us to drastically increase the overall performance of the system. So if we want to kind of see how that works, is here we have 4 different cores, each core having direct L1 memory built onto the core. Attached to the core is additional L2 cache, which is just, again, temporary memory. And then between each of the cores, there is the shared L3 core, or L3 cache. That way, any of the cores can access that shared cache. It's also important to note that all of them have direct access to the memory controller as well. So as we start talking about different types of processors, we have to get used to the families. And all that is the architecture. Here the family is called Ivy Bridge. They're the 3rd generation processors of the I series. And that's the Core i7, Core i5, Core i3 series. So we call that a processor family. And that is the speeds of the processor up to 3.9 gigahertz. But the important thing here is how much cache does the processor have. Notice it has 8 megabytes, not bits, but bytes. Next, it can handle either 133 or 1600 megahertz DDR3 type memory. The important question here is not question, but the thing to note is the dual channel memory. We haven't gotten the memory just yet, that's at the end of this chapter. But dual channel memory is essentially 2 things of memory working in tandem so that they can get done things, they can complete tasks quicker. Here is a chart for the different types of families of, again, Intel-based processors. 2nd generation, that family was called the Sandy Bridge. Or the 1st generation is called, actually I don't remember what the 1st generation of i7s were called. But those are just previous versions. The important thing for here to note is just the architecture. As the processors get redesigned, they get into a different generation, and the functionality might change. So that's important. Processor identification. Currently for Intel, it is working on the processor numbers, and that is like an i7-920 or 940. All that really means is i7 or i5 hyphen the generation. Now, we just focus mainly on the i7s, i5s. However, what about laptops? Laptops also have processors, but here we have to think about the characteristics of processors for a laptop versus a desktop and why they might be different. Here we talk about the Centrino technology, and essentially that's just a technology built into processors for mobile markets. Mobile market being just laptops or tablets. They actually allow for better integration between the processor, chipset, wireless, for all of these interconnections between all the devices, where they might not run as fast, but they consume less power. The fact that they consume less power means overall the laptop or the mobile device stays on longer. So now that we talked about Intel, we can focus on some of the AMDs. Again, AMD, same structure. As they go through different editions or different generations, there are different families. Here we have the Black family and the Phenomenon family. Then we have the Athlon family and the Sempron family. And again, these are just a few of the AMD processors that are out there. Actually, if we were to list them all, it would be a fairly large list. The important thing when we talk about processors is match up our motherboard with our processor so that they work together. Now, which one is better? That's too subjective to answer, but do your own research and find your own conclusion. So, the reason I said find your own conclusion is because you're going to be asked as a PC repair technician, what's the best? Well, how do you select it? How do you install it? Well, the selecting is pretty easy. Match your user's needs and probably match, again, their already existing components. If they have a motherboard and they don't want to spend too much money, you could probably upgrade the SD processor in the motherboard. Which means you'd have to find the motherboard, find out what processor it supports, and get a newer version of it, assuming that it will work. If it's too old, you might have to get a new motherboard and a new processor. But again, you pair the two. That way the motherboard and processor go hand in hand. The important part for this is knowing how to read and how to match our processors to the actual motherboard. And all of that goes back to reading the documentation. Next, how do we install a processor? And it's pretty straightforward if you've never done it. You remove the old one, or if you're installing a new one, you install the motherboard and then you put the processor in. You do not force it, you go in nice and easy. We're going to do this as a lab, and we're also going to talk about it a little bit further in greater detail, but it really isn't overly hard. While yes, you do have to be careful, that's it. As long as you're careful and you don't go too fast, there shouldn't be a problem. So the first requirement we have is, again, make sure our motherboard and processor support one another. Also, when you're talking about selecting, match the user's needs with the processors that are out. So that probably means you're going to have to be on top of your game with knowing what processors are currently out on the market. Intel, I know, does a lot of free training so that they'll cover all of their processors, all their processor types, all of the new features of the processors. Intel goes all out. That way people can sell their processors. AMD, I would imagine, also does the same thing. I'm just not sure where to find the videos. If you Google Intel Retail Edge, there are a lot of videos that Intel puts out for specifically that reason. Okay, so now let's talk about the installation process. First step, read the manual. Make sure you read the manual for the motherboard, read the manual for the processor, make sure you have everything ready to go, and you're going to be following directions. Next, ground bracelet. That also means take off your jewelry, prep for dealing with sensitive components. Protecting the component and yourself from ESD is extremely important. Next, assuming that the motherboard is already installed, even if it's not, if it's on an anti-static bag, we're going to be opening the socket, and we do that by normally pushing down the lever that will hold the socket closed. Once that socket opens, there might be a load plate there might be a plastic protective cover. We will remove that plastic protective cover. If it's not there, then don't worry about it. Sometimes it's there, sometimes it's not. But once you remove that cover, we will hold the processor from its edges above the processor slot, verifying that the markers on the processor line up to the socket. For example, with this motherboard, we have an arrow, and there's an arrow denoting on the socket bottom left-hand corner. That way you can verify that those parts are lining up. There's also notches on the side that prevent you from installing this incorrectly. Do not force this. If it doesn't go in easy, stop, pull it out, look at what's going on, and try to find out why it's not going in. Most of the time, if it's not going in easy, it's due to someone putting it in backwards. That's fairly common. But again, look at the notches and look at the processor. Make sure the notches line up so that you cannot incorrectly install the processor. That is also making sure that the processor is aligned correctly. Once you're verified that it is aligned correctly, you would lock the processor in by lowering the lever. Once that's done, we have to talk about how to install the cooler. And that is, again, pick a cooler that works with your motherboard. Understand how the cooler posts work. How does it connect to the motherboard? Step 2, apply thermal compound. That may or may not be necessary depending on the processor cooler that you have and if it's already pre-applied. Now remember, the thermal compound is a compound that will separate the processor from the fan that will help transfer the heat from the processor to the fan. We'll do this as a lab just so that you can verify how much you need. Once you've applied it, you will verify that the posts for the cooler are connecting to the motherboard, and you'll be locking them. You'll be locking them by pushing down at each of the locking pins until it either pops or it locks into place. Once you make sure and verify that the cooler is properly seated, you want to plug it into power. That way, well, it has power. Also, you'll check the BIOS to verify the system recognizes the processor and the fan. Here's the example of our BIOS, and this BIOS recognizes a i7-920. So assuming that was the processor we installed, we should be good. Now, installing other variations of the processors, it's the same thing. It's just, again, read the documentation. Do not bend the pins. Be careful. Protect yourself from ESD. And verify that the notches line up and install the new processor. Notice here we have a notch in the processor and we have a post in the socket. If you try to install this backwards, the notches won't line up. You can't fit the processor in. Here are the instructions once more for a different type of processor. But here, still an LGA, so that means typically no pins. But again, you line up it, you read the documentation, you line up the processor, you install it without doing any pressure, and you lock the lever. Now here is a PGA, a pin grid array type processor. This one has pins. Notice that the lever up, the top plate shifts. So how do we install this is, we put the processor in the socket, lining up the notches and verifying that we're not pushing on it, but I mean, it just goes in nice and easy. Once we verify it went in nice and easy, you'll lower the lever. Lowering the lever actually locks those pins in place. Here it is once more, but here this is the pin grid array one, and that is you lift the lever, you place the processor, verify processor pins are sitting slightly in the hole, that you're not forcing them, that you've lined them up, and as you slowly push the lever down, it should lock into place. Apply the thermal paste and the cooler, connect the clips, test for power, verify the processor works. The processor installation guide is the same regardless of the processor type that you have. So now that we talked about how to install a processor, let's talk about our memory. And our memory stands for Random Access Memory, RAM, and that is, again, temporary storage for our processor. Now we have to talk about two types of memory, and that is static RAM or dynamic RAM. And now remember, both are volatile, which means if there's no power, there's nothing there. However, static RAM functions different than dynamic RAM. Dynamic RAM functions where it can be dynamically changed on the fly. Static RAM cannot. So when we talk about our typical desktop memory, we're talking about dynamic RAM or DRAM. Notice in the diagram we have two black slots and two blue slots. We kind of talked about our dual channel memory, but now we're going to start getting into it a little bit more. All our dual channel memory is it's two matching memory slots as long as the documentation supports it. But it's two or more memory slots that are the same color working together. The fact that they're working together allows them to function faster. Now, there's dual channel or tri-channel or quad channel, so it all depends on how many RAM slots there are and if they're the same color, as well as the documentation is showing that it supports either dual, tri, or quad. Other variations of dynamic RAM are our DIMM, which is a dual inline memory module. And that means basically inline memory module being memory on both sides. Small DIMM, and that's SODIMM, typically used in laptops. Lastly is our RAM and SIMM. Our SIMM is our single inline memory module. Not really used anymore. But the main differences between our DIMM, RAM, and SIMM is the data pathway that they can communicate with, and how fast or how much data can the memory module process. Those are the main differences between our DIMM and RAM and SIMM. Again, DIMM is our newest type of memory, and that's what our standard is right now. So now that we talked about DRAM and we talked about DIMMs, now we can talk about the different styles of our memory, and that is the different generations. So we talked about our DRAM, and our DRAM actually was our memory of choice early 90s, mid 90s, but it wasn't quick enough. So what we did was we had to get double the amount of memory. So I'm actually going from the bottom up. So I'm looking at the second from the bottom, the 168-pin SDRAM. And that is older memory that's slow. So what we had to do is we had to have a way to double the memory. And what we did was we created DDR. And all that is it's a way that the system could access the memory twice as fast. Hence the double data rate SDRAM. But it got to the point where our DDR RAM wasn't fast enough, so we came up with DDR2 and then DDR3. And for our system memory, we're at DDR3 right now. As we need more memory or faster memory, we might go to DDR4, DDR5. It really all depends. Now let's talk about the last option, RAM. RAM is a special type of memory that was a fad that never really caught on. It was produced for a lot of Intel-based products. It was faster than our SD-RAM. It was just, well, it was expensive and it just wasn't as popular. So once we came out with DDR, our RAMs kind of just went away. Here's an example of our SIMs, and that's again just a single-sided inline memory module. It's memory just on one side typically. So the important part for our DIMMs. Our DIMMs normally use a 64-bit data pathway. It's just, again, the communication pipeline is 64 bits long. It has interdependent pins on opposite sides of the module. That way they can access data twice as fast. One pin on one side accessing one bus, one pin on the other accessing another bus. While older DIMMs were asynchronous to the system bus, our SD-RAM ran actually synchronous with the bus. And that is everything running at a standard time. So again, we had our synchronous dynamic RAM that we needed faster and faster, hence the double data rate, DDR. I've never really seen it referred to as SD-RAM 2, but you never know. We love our acronyms, so normally when you talk about memory, you just talk about DDR1, DDR2, DDR3. You drop the SD-RAM. You don't call it SD-RAM 2 or SD-RAM 4. But the important here is, with each new development of faster memory, we got ways to get them faster and to use less power, becoming more and more efficient. So let's talk about other factors that may affect the capacity, features, and performance of our memory. And that is, again, the number of channels. That's, again, how many sticks that we have working together, how much memory is on one actual module of memory, its speed, if there's error checking, or if there's buffering involved. The error checking actually is one of the key things for speed, because if we have to double check all of the items in memory, it slows down the memory. For an everyday computer, normally we don't do memory checking or error checking. However, for servers, we have special memory that does do error checking. It really all depends on your requirements. Now, early single-channel DIMMs, that's just one module working individually. The memory controller is accessing the one DIMM at a time. However, with dual channel, the memory controller can access 2. Tri-channel, the memory controller can access 3. Quad channel, it can access 4. So again, with it being able to access more than one module, it can work. The modules can work in tandem, which means work can actually get done quicker and quicker. Quad channel again, 4. Current generations of i7s or a current generation of AMD processors can handle quad channel, and that is 4 channels working together. So how do we set up our dual channel, tri-channel, quad channel? You check the documentation to verify that the motherboard supports it, and then you follow the instructions in the motherboard. In this example, it's 2 black, 2 blue, and so you line them up. 2 in blue, 2 in black, thus dual channel. However, don't always think about the color being the definition. Check the manual. Don't just assume that the colors show that it's dual channel. What about tri-channel? Notice here there's 3 blue slots, 1 black slot. So what happens if we had memory in all 4 slots? The 4th channel really just wouldn't be used the same as the tri-channel. It's actually more efficient to just do the 3 slots, not all 4. So let's talk about our DIMM speeds. How do we measure our speeds? Normally it's measured in one of 2 ways, either megahertz or PC rating. The PC rating is the total bandwidth between the module and the processor. Normally it's a PC2-64000 or 13333. Again, that is just the total bandwidth between the memory and the processor. Other ways to verify the speed is actually just a megahertz. DDR3 right now comes in 16,000 megahertz modules. Now the PC rating is not 16,000 megahertz. It would actually be PC3-bandwidth. We've already talked about our single-sided DIMM. What would be a double-sided DIMM? That would just be modules on both sides. We've already talked about the memory bank. We've already talked about the dual banks. Again, the bank of memory is just the actual memory chips on the actual memory module and how we can address those modules on a module. If they're single rank or if they're dual rank, and that is, can we access just 1 rank on the module or can we access 2 ranks on the module? Now the important topic, error checking. So here's an example of our error correcting code, or ECC. Again, normally our desktop memory does not use ECC or parity error. This is all server memory technology. And this is just special ways to verify that the information in memory is 100% accurate, correct, and has no errors. Now this can be done again in error ECC mode or parity mode. But there's other ways for server RAM to function. That's either registered, unbuffered, or fully buffered, or with registry support. Again, this is all server grade memory technology and is different and will have different notches than what's in your traditional PC memory. Just like anything else, you line up or you match the memory with the documentation. Because each one of these has specific notches. So if the motherboard supports full buffered memory, you're only dealing with full buffered memory. You cannot stick any other form of memory module in there. It has to be whatever the motherboard is used to or designed for, not used to. So how do we actually talk about the speed of our memory? We talked about like its bandwidth, we talked about its megahertz, but how do we actually say how fast the memory functions? So when we talk about latency, that's the delay within our memory. And that is how can we access the different rows and columns of our memory. Again, memory is just like this huge spreadsheet with rows and columns, and we stick data in different cells. That's a junction between our row and our column. And we measure this in 2 ways. Column access, or CAS, or row access, which is RAS. And this is the delay going between the columns and our rows. Now, how we actually verify the speed of our memory is we look at our CAS, our column access. And normally to denote it is 4 groups of numbers. For example, 5, 5, 5, 15. And that is just the speed of our memory. The lower, the better. So really you want like 333-15. However, you will notice that with DDR1 and DDR2, we could have lower CASs. However, the actual speed of the memory was lower. Granted, now with DDR3, our numbers may be higher, our CAS is higher, however, the speed of the memory is also now faster. So you have to factor both of those in. You want to look at the CAS as well as the megahertz of the memory. So now that we talked about our traditional type of memory, we have one more set of memory we have to talk about, and that is our RIMs. And that is actually tied directly more with our Rambus RAM, and that is again Intel proprietary type memory. And this was done in pairs. You had to do this in groups of 2. If you had just one, you'd have to have a blank memory stick so that, again, it would always be in pairs. Our Rambus RAM kind of kept up with our DDR and DDR2. It's just, again, it's very proprietary, it's not very open, and it's not as widely used as our traditional DRAM or our DDR RAM. So now that we covered our basic memory, what are some factors to consider when we talk about how do we install or recommend our memory? And that comes in a few different ways. First of all, how much memory do we need? What memory technologies are we using? What speed is the memory? Do we need error control or not? Or are we also going to be talking about single, dual, tri, or quad channeling? A big part of this is, if we're dealing with home users, what are they doing? So that kind of gives us how much memory we need to get. But everything else is kind of tied directly to our motherboard and processor. If the motherboard supports dual channel or triple channel memory, then we'll probably be going with dual or triple channel memory. If the motherboard doesn't support it, then we'll be going with it. However, more common motherboards nowadays, you're looking at either dual, tri, or quad channel. That's a standard. And again, faster memory the better. More memory, typically the better. But not always. It will get to the point where adding more memory won't actually improve any performance. For example, my computer right now, I had 32 gigs of memory, and I doubled that to 64. There was no speed improvement whatsoever. 32, even 16 gigs. There really wasn't a whole lot of improvement between our 16 going to 32 gigs. And going from 32 to 64, there was even less of an improvement. So you look at what you're going to be doing, and you get memory based off of that. Typically in today's market, you're looking at least 8, 12, 16 gigs of memory at least, just because of how cheap memory is. Also bear in mind that our memory connectors are gold, typically, and be careful, you don't want to touch them, because again, your oils on your fingers are corrosive and could damage the memory module. Adding memory is pretty straightforward. You check the documentation, you see what's supported, you verify there's an open slot, you put new memory in. It only goes in one way, and verify that you install it without forcing it in. Also, it's important to note, verify that the PC is turned off unplugged, has no power, before you try doing any of this. I've had a few people that tried to install memory with the PC on, and it destroyed everything. So make sure the PC is completely off, unplugged, disassembled as much as you need to before you install the memory. A big part there is, again, verify that it's unplugged at least. So what are some problems upgrading memory does? If this computer is overly slow, adding more memory may help. Applications that need more memory to run may not actually load unless you have enough memory. If your computer is unstable, keeps turning off, could be memory. Not always, but I mean it could be. Memory, again, all around just helps. So again, when we talk about upgrading, the first important question is how much RAM or how much memory do I actually need? What kind of memory? Am I purchasing the right modules? Is there enough physical slots to install the new modules? Keeping in mind, when we brought up that 32 versus 64-bit memory, 2 to the power of 32 bits is around about 4 billion. So if we're running a 32-bit operating system or 32-bit processor, we can only install 4 gigabytes of memory. That's all the memory that it can handle. However, if you have more than 4 gigabytes of memory, if you install a 64-bit operating system with a 64-bit processor, you can have a lot more memory than just that. So if you have anything over 4 gigs of memory, you have to have a 32, or you cannot have a 32-bit processor and 32-bit OS. You have to have a 64-bit processor and a 64-bit OS. 32 bits limit how much memory you have. If you have a 64-bit processor and a 32-bit operating system, and you have 16 gigs of memory installed, the operating system will only ever use less than 4. I kind of disagree with this. How much memory do you need? All you can get, again, it really all depends on what you're doing. More is not always better. I got 64 gigs of memory, and I can't tell the difference between that and 32. I can barely tell the difference between 16 and 64. Again, it really all depends on what you're doing. So, other questions is how many slots are filled, brands. Branding is important because some brands are better than others. Some brands are better quality. Some brands are poor quality. It really all kind of depends. Also, read the documentation both on the motherboard, processor, memory, just to verify that it all works together. Normally, if you're reading just a motherboard manual, it will tell you what memory it supports, and then you can just get memory based off of that. Read the motherboard documentation. This is so critical, and yet this is something that most people fail to do. Most DDR3 boards do support dual, tri, and quad channel memory. Again, if it's tri-channel, the motherboard manual will say tri-channel, and you get a tri-channel memory. If it's dual channel, you'll get dual channel. If it's single channel, you'll get one channel. If your motherboard does support tri-channel, you want to make sure that you're getting 3 memory modules that are the same speed. Realistically, if you get tri-channel memory, you can actually go online and buy specifically, the packaging will say tri-channel, and that will be 3 identical memory modules. While you do not have to use 3 identical memory modules, best practice is to get 3 matching ones. Same thing with our dual channel. If it's a dual channel, you want to get dual packaged memory. Again, that's just 2 memory modules that are identical. I will let you guys read this. Again, this is all just going back to what motherboard supports what type of memory. Read the motherboard documentation. RIMS modules, they're no longer made. They're being replaced. They're old. They don't function. That's a big thing. If you cannot get matching modules, compromise, but you want to get as close as possible. Realistically, with how cheap memory nowadays is, buy them in matching sets. It's actually going to work better for most people. Do your research. Go to your whatever purchasing website that you want and do your research. You can actually verify that these memory modules come in sets of 2, 3, or 4, or whatever your needs are. Just you have to look. So how do we actually install it? Use your grounding bracelet, take off your jewelry, turn off the power, handle the memory module with care, don't touch the metal contacts, don't stack the memory modules on cards or other modules. That's kind of subjective, but I mean, be careful with them. Line the notches up and install. You'd install DIMMs the same way. If the memory module is not all the way down, it won't work. It won't damage it. It won't work. The motherboard will actually, when you hook it all back up and you turn it on, it will actually say memory error. How do we install our RIMs? You follow the manual. Don't always begin with 0. You look at the manual, you verify the documentation, and you install it according to the documentation. And that's it. So if you have any questions, email me or let me know, and we will go through this. I want to thank you, and I hope you guys have a great night. Bye.